Okay, guys, welcome. So today we're going to talk about an application of non-homogeneous second order linear ODEs. And that's the idea of extending on the previous video that we did for unforced oscillations for a mass spring system. And now we're going to talk about the non-homogeneous version, which now means that your oscillations are forced in some way. So this, again, is essentially saying that we're looking at our familiar mass on a spring system where, of course, if you have some sort of damping, then that is the dash pot at the bottom there. Now, again, so the idea is that we're going to extend this by now introducing a forcing function, which is R of t. So this is some sort of external force function here. And this, of course, is now going to change the dynamics of our mass spring system. So for our sake, we're going to consider a special type of periodic external force, and it's going to be given by some F0 times cosine of omega t, right? So then what we're essentially doing is we are solving the non-homogeneous ODE given here, right? So our R of t is equal to this F0 times cosine of omega t. So what we are going to do in order to find the solution is we're going to use the method of undetermined coefficients, right? Because after all, we have that M and C and K are all constant coefficients, right? So we're going to let our particular solution be, again, we're going to have the solution of the homogeneous version, which if we saw before was A times cosine of omega t plus B times sine of omega t. And then if we plug this back into our function, we get a big mess of terms here, but we're going to eventually find, and again, this is something that you should verify on your own, and we are equating the cosine, or grouping the sine and the cosine terms together, and then equating coefficients, right? So we have cosine over here and no sine. So we get that everything in front of the cosine has to equal F0 and everything in front of the sine has to equal 0. So I'll spare you all the details of the algebra, but you can eventually find that A is equal to F0 times K minus M omega squared all over the quantity K minus M omega squared all squared plus omega squared C squared. And then, of course, similarly, you can show that B is equal to F0 times omega C over the same denominator. Right. Of course, this is all assuming that that denominator is non-zero. Okay, so as we did in the unforced mass spring system, we're going to let the square root of K over M be omega 0, so that way we can say that K is M omega 0 squared. And now we have these new formulas for A and B, which is what we're going to sort of stick with here. Okay, and this should be omega 0 here. That's maybe not the clearest. Okay, so again, we know that our general solution is made up to the general solution of the homogeneous ODE, and our particular solution is this horrific mess right here. Right, since we solve for A and B in terms of those other quantities above. All right, so that's what our solution form is going to look like. So of course, now there are two different types of forced oscillations, right? So just as we did before, the first thing that we're going to do is we're going to consider the undamped oscillations. And again, in this case, they're forced. So just as before, of course, can't eliminate 100% of the damping, but if the damping is small enough to where we can neglect its time over the time period we're considering, we can essentially assume that the C term is essentially zero, right? So what happens there is that if our C is zero, if you plug zero in for C in each of those coefficients, you get that A is equal to this quantity here, and that B is equal to zero, right? And then that allows us to say that our particular solution is given by these two forms. Oops. There we go. So these two forms here. Okay, now of course, in order for this to be valid, we of course would need that omega squared is not equal to omega zero squared, all right? So that we have something that's valid there. So now the frequency of our cosine, which of course is W over 2 pi, if you remember your sort of your trig facts for the period of sine or cosine, is going to be different from what's called the natural frequency. And again, that's because of the difference between omega squared and omega zero squared. Okay, so now the general solution of the undamped system looks like this. And again, this first part is coming from what we did before. That's the homogeneous solution. And the second part is the particular solution that we sort of just discussed. Okay, so, and again, this is one note here that this is just a superposition of the two harmonic oscillations of the two frequencies that we've sort of talked about. Okay, so now the next thing that we need to discuss is what's called the resonance, right? So the maximum amplitude of your particular solution can be found by putting cosine of omega t equal to its maximum, which of course is 1, and you get that the maximum amplitude is given by f0 over k times rho, where rho is 1 over this 1 minus quantity omega over omega 0 squared. Right? So of course this depends on omega and omega 0. So if your omega is tending toward omega 0, or your omega is tending towards the frequency for the homogeneous version or the unforced version, then A0 is going to tend to infinity, right? So that's what we essentially call the resonance, right? So you're getting sort of this excitation of large oscillations because your frequencies, your natural frequency and your other frequency, we're just calling it frequency here, your natural frequency and your frequency are becoming equal, and that's referred to as the resonance. Now this term rho here up here, this is called the resonance factor. Right, and we'll see later that rho over k, which is equal to A0 over F0, is the ratio of the amplitudes of the particular solution and what the input is, right? And this is going to be something that's going to become important as we study this particular phenomena. Okay, so in the undamped case, of course, we lose our C term, and this is our non-homogeneous ODE, right? So the solution that we found before is no longer valid, but we can use the modification rule to find that a particular solution is now of this form, right? Basically what we're doing is we're just now multiplying by t. Okay, so now if I call my undamped forced oscillation ODE star, if we substitute this particular solution into star, you would get that A has to be 0, so your cosine term drops out. And your B, it can be found that B is equal to F0 over 2m times omega 0. So this gives us our particular solution as listed here, right? So basically what happens is that this particular solution, you have resonance because your oscillations are getting larger and larger as time goes forward, right? Because, and essentially what this means in a practical sense is that if you have little to no damping in a system, basically what's going to happen is that you're going to, by forcing the oscillation, it's going to get sort of out of control, right? And it's going to cause the system to sort of break down. All right, but this is another thing that we'll sort of come back to later. Now, another thing that is interesting is that if your omega and your omega 0 are close together, and we're assuming in this case that we have a particular solution that looks something like this, then what's going to happen is that you have the period of this sine function being large. So this has a large period, right? And what's going to happen is that you get this type of oscillation here, right? And this is sort of indicative of what sort of like, so this is like an example of what like sound waves look like. And the book says here that in this particular case, this is like what musicians listen to when they tune their instruments, right? And again, the idea there is that the frequencies are close together because they're trying to get the two tunes to basically match pitch, right? So those things should not be, you know, ideally they want them to be exactly the same, but of course you can't get them exactly the same, so you get that as small as possible, which leads to the omega 0 minus omega being very small. Okay. So of course, now we can look at the more interesting case. We can look at the damped force oscillations, right? So if now we're considering not negligibly small damping, so of course now we have a positive C value, and we pick up a damping term in the ODE, right? So again, in this case, you have that your solution is y equals yh plus y sub p. And since yh goes to 0 as t goes to infinity or x goes to infinity, whatever you're letting your independent variable be, you get that y approaches y sub p, which is the steady state solution. Right, so after some time, because of the damping, you're going to settle into some sort of fixed state after some point, right? And that's what this theorem says, that after a sufficiently long time, the output of a damped vibrating system under some sort of sinusoidal driving force will get a harmonic oscillation whose frequency is whatever the input is, right? Because your homogeneous solution is going to eventually decay to a point where it's not affecting your input oscillation. Okay. So of course, this is going to be different from the undamped case because the amplitude of your particular solution in the undamped case approaches infinity as omega and omega 0 get close together. But this, of course, doesn't happen in the damped case, right? So when you have a damped system, the amplitude is always finite, right? Now, on the other hand, it may have a maximum for some omega depending on the damping constant C. And this is what we tend to call what's called practical resonance, right? Because if C is not too large, then there's some input that might get your oscillations large enough to damage or destroy the system. And this has sort of happened before in physical settings where we didn't know as much about resonance, but now this is something that we sort of, can avoid. Okay, but anyway, so we're going to look at our particular solution in this form, where we have C star times cosine of omega t minus eta, and our C star is the amplitude of our particular solution, and eta is the phase angle, or phase lag, because it measures the lag of the output behind the input, right? And you can see that sort of in this sentence here. Okay, so it can be shown, and for time's sake and sanity's sake, I'm not going to go through the derivation because we saw that A and B are, quite long, but we can show that C star depends on omega and is given by this quantity here, and that the tangent of eta is also dependent on omega and is given here. Okay, so that's going to be important moving forward. And so essentially the idea is that we want to find out whether or not that there is a maximum amplitude of our particular solution, right? And so to do that, we can look at the derivative of our C star and set it equal to 0, just like we would in a Calc 1 setting, right? So if we take our derivative of C star with respect to omega, we get this hideous expression here. Now, of course, this is only 0 if this expression in the brackets is equal to 0, and that will only occur if we get that C squared is equal to 2m squared times the difference of omega squared and omega, right? And of course, don't forget that omega is square root of k over m. Omega 0 is square root of k over m, so if you square it, you just get rid of the square root, right? So if you reshuffle terms, you can arrive at this statement here. And of course, it's nice to think of it as 2mk times c squared, because this will be negative if c squared is larger than the other side, right? C squared 2mk, right? So if c squared is larger, then there's no real solution, and you get that C star decreases as omega increases, right? And then if C is smaller, then there is a real solution where you obtain the max, and then that's given by this value here, right? So of course, this solution will increase as C decreases, and of course, it's going to approach omega 0 as C approaches 0, right? So, and that makes sense, because if C approaches 0, that means that you're eliminating the damping, and that you get that the maximum is going to be the same as the sort of the natural frequency. Okay. And this is showing for how the sort of the damping constant plays a role in the amplification, right? So that is so that's something that's helpful to us. Okay, so now we can talk about the amplitude being obtained for the specific omega value that gives us the maximum. So if we plug in this information into our equation that we have above, we can find that our maximum amplitude is going to be given by this 2m times f0 over this c times the square root of 4m squared, omega squared minus c squared. Now, of course, if c is strictly positive, then we always get that this is finite, right? And of course, since our expression in the denominator decreases to 0 as c squared goes to 0, then the maximum amplitude increases towards infinity, right? Which makes sense with what we talked about before. Okay, so the last thing that we will comment on here is that this this last graph here is showing the relationship between the phase angle and our frequency, right? So if the phase angle is less than pi over 2, then that indicates that your omega is less than omega 0. And then, of course, it's going to be greater than pi over 2 for omega greater than omega 0. Okay, so that is some of the application of what happens when now you have a forced oscillation in this mass spring system. So I hope you enjoyed the video, and I will see you next time.